This lecture is on the third section of chapter 2. It's about evaluating limits analytically. Another word is finding the limits of functions using algebra. So let's start with example number 2 in this lecture note. You're supposed to find the limit of 3 when x goes to 2. And again, 3 is a horizontal function. Right? It's continuous everywhere. That means when you find the limit of these functions at 2, the limits of these functions is always just the values of y, so which is 3. It's always 3. And then you want to find the limit of x to the 4th when x goes to -1. If you think that if you plug -1 into the x, and you don't have any problems by plugging in those functions, then you should go ahead and plug the value of x into the functions to get the limit of the function when x goes to -1. So we get 1. Number 3, again, if I can plug 2 into the functions without any problem, right, without running into a problem, then I should plug it in and evaluate this limit by plugging in. For sine of x, I plug sine of pi is equals to 0. Okay. Number 4, if I plug 1 into the functions, I don't have any problem at all. So this should be 2, -4, -2 over 2 is -1. And then what is the secant of 0? Secant is 1 over cosine. So cosine of 0 is 1. So it should be 1 over 1 equals 1. All right. So this method of finding limits using plugging in the values of x into the functions is called direct substitutions. It's called direct substitutions. And when can you use direct substitutions? You can use direct substitutions when the function values of f of x is the same as the limit of f of x as x approaches to c. In other words, if you plug the value of c into x and you can find the values of f of c, that means you can find the limit of the functions f of x when x goes to t, when x goes to c is the same as the value f of c. Right. Then we can talk about the properties of limits. There's a theorem 2.2 in your textbook. If you have b and c are real numbers, and n be a positive integer, and f and g be functions with the limit, we know that the limit of f of x when x goes to c is L. We know that limit of g of c when x goes to c is k. Then the following 5 properties will satisfied. First, the first property is scalar multiple. It says if you want to find the limit of b times f of x, where again b is a constant, f of x is a function with this limit, when x goes to c, it will be the same as b times L, where L is a limit of f of x when x goes to c. If you add or subtract f of x and g of x, then the limit of the sum of f of x and g of x, or the difference of f of x and g of x when x goes to c, is the same as the sum or the difference of L and k. Again, L is the limit of f of x, and k is the limit of g of x. Similarly, if you multiply the two functions together, when x go to c, the limit of this product is going to be the product of L times K. Quotients, when you divide f of g by f of f, when you divide f of x by f of g, then the limit of f of x divided by f of g when x go to c equals to L divided by K, where K is different than 0. And the last one is a power rule, right? The power properties is saying that if you find the limit of the function f of x raised to the n when x go to c, then it's the same as L raised to n when n is a positive integer. Now we can use these properties to find limits of this following example. We know that in this case, now that the limit of f of x when x go to c is 4, and the limit of g of x when x go to c is -3. Then the first limit is asking to find the limit of g of x raised to 3 when x go to c, using the power properties, right? You can take -3 and you raise to 3. Number 2, limits of 3 times f of x, where 3 is a constant, so you use a constant property. It's just going to be equal to 3 times the limit of f of x, which is 4. Number 3, find the limits of this product of the two functions, f of x and g of x. You know that you have to use a product. And the products of these two is 4 times -3. Number 4, the limit of 4 minus f of x. That means you have limits of 4 is always 4, right? And limits of f of x is 4. So you get 0. Number 5, the limits of the sum. So you have 4 plus -3. Number 6, you have 2 times x, 2 times 4 divided by negative of -3, which is a/3. If you do this, you will have -12, 12, and -27. This is how you use this above properties to find these limits in the third example. All right. Next, we can talk about the limit of composite functions. So that's a theorem that you can apply to find the limit of the composite functions if the two conditions satisfy. So let f and g are functions such that the limit of g of x when x goes to c equals to L. That means the limit of the functions g of x when x goes to c exist, right? And the limit of f of x when x goes to L equals f of L. That means you can find the limit of the function f of x at L by plugging this big L into the function x to find its limit. Then the limit of the composite functions f of g of x would be equals to the function f of the limits of g of x when x go to c. And since we know that this limit here is L, so then you just need to plug L into the function f to get the limits of these composite functions. All right, another way to see this theorem is when you need to find the limits of the composite functions, and once you have these two conditions satisfying, then you can just pull the f here out in front, right? And then, let's see. You pull the f out in front, And then you evaluate the limit of g of x when x goes to c. And then you just need to plug this whatever value for this limit into the function f to get the limits of these composite functions. Now let's look at this example. So you have two different functions, f of x and g of x. Let's say f of x when x, the limit of f of x when x goes to 1, we can plug it in. So then it's going to be 3, right? And then you want to find the limits of g of x when x goes to 3, which is, you can still plug it in here to get square root of 4 equals to 2. Okay. And then the next question is, what is the limit of this composite functions here? Let me check. Can we pull the g out? So using the theorem, we can try to pull the function g out and then find the limit of f of x when x goes to 1. And let's look at the first part here. The limit of x when x goes to 1 exists, which is equals to 3. And also the limit of g of x when x goes to 3 equals to 2. That will help me to know that, so this and this are the same. Know that the limits of this function will be equals to these values, equals to 2. All right. Now that we have talked about direct substitutions, we talk about finding limits of composite functions when it satisfies a couple of the conditions. Now let's revisit the second example problem number 4. In this problem, I changed the point of interest to -1 instead of 1 earlier. Remember, in example number 2, we find the limits of these functions when x goes to 1, right? And then we just plug it in there, plug it in the functions to find the limit. In this case, you cannot do that because when you plug -1 into the x, you will get 0 in the denominator. So you cannot plug -1 into this function to find this limit. What else can you do? In this case, luckily that I can see, I can do something else. I can try to factor the numerator out. So if I can try to factor it out, I will get 2x, right? And then x over x plus 1. So when I factor it out, it should be -3 plus 1. Because -3 times 1 is -3. And when you multiply 3 times -x, you get -3x, and you multiply this here, you get 2x, so -3x plus 2x is -1x. So this factoring works. And since this works, and I say, oh, what else can I do? I can get rid of x plus 1 and x plus 1 here. And now my functions is left with just 2x minus 3. And if I can plug -1 into the x here to get to the limits of these functions. At first, I could not plug -1 into this original functions, right? But then after factoring out the numerator, after canceling the term in the denominator, I can actually plug the -1 into the new functions, the functions that are very, very similar. So these two functions are very similar to each other. They only difference at one point, which is x equals to -1. At x equals -1, this function is not defined. But at x equals -1, this function is defined. All right, so I found my limit. And then how can I know that this limit here is the limit of this original functions? I know that because I can use this theorem. The theorem 2 says that if the two functions f of x and g of x are equals to each other at all x values except possibly at c, right? So they agree on a lot of values except one or a few values. In this case, except possibly at c when they not agree on, then the limits of the function f of x when x goes to c is the same as the limits of the function g of x when x goes to c. Okay. Using this theorem, I know when I can use algebra to simplify my functions, right? To simplify from this functions down to this functions. So then I can find the limit of my original functions using the limit of the function after I use some algebra, manipulate algebra to get to the new functions. The function that is similar to find the limit of. Okay. So in strategies for finding limits analytically, there's two main techniques that you can use. The first technique is called dividing out or canceling a factor technique. This example here illustrates the dividing out or canceling a factor technique. So I did actually cancel this factor here. I cancel the denominator so then I can plug the -1 in. Okay, let's do an example. So again, you cannot plug 1 into x because it would make your denominator equal to 0. So then you have to see if you can factor the numerator out. So I have x to the 4th minus 1. And I don't know if you remember, but there's a formula that tells you if you have b squared minus a squared, be the same as a minus b times a plus b. So I'm going to use this formula, and I'm thinking that my x squared is x to the 4th, and 1 is actually just 1 squared. So it's going to be equals to x squared minus 1 times x squared plus 1 divided by x minus 1. And at this point, I still cannot plug 1 into the x because I need to get rid of this. I need to get rid of this term right in the denominator. And then I say, oh, I have x squared minus 1. Using this formula again, I can keep factoring x minus 1, x plus 1, x squared plus 1 divided by x minus 1. So this term becomes these two terms. And at this point, it's like, oh, I see a common factor here, x minus 1 and x minus 1, so I can cancel it, this term. And what left over is x is 1, x plus 1, x squared plus 1. Okay, now is the time when I can plug 1 into the x's to find the limit. So 1 plus 1, 1 squared plus 1, the answer should be 4. So I use the canceling a factor technique to find this limit. And the second technique is rationalizing technique. That means when you see radical form like this and like this, you can think of multiply the whole functions by the conjugate of this numerator. Okay, but let's look at the limits first. X equal to 0, you cannot plug it in. So I have to do something else. I have to manipulate algebra if it's possible. And again, I see the radical here in the numerator. Then I'm thinking about maybe I'll try to multiply the whole function by this not numerator's conjugate. So the conjugate term of square root of x plus 5 minus square root of 5 is square root of x plus 5 plus square root of 5. Okay, they call it conjugate because when you multiply these two terms together, you will get rid of the radical terms. All right, let's multiply them together. I multiply 2 both numerator and denominator by the numerator's conjugate term. Okay, and then when I multiply this together, I will get, so you can see that this is a minus b times a plus b. A minus b times a plus b equals to a squared minus b squared. And the result should be a squared minus b squared, and there's nothing change in the denominator. All right, and I keep simplifying. So the square root of x plus 5 squared is just x plus 5, and square root of 5, which is 5, and you have x. And then you have this, can cancel this, right? 5 minus 5 is 0. So then x go to 0. X over x, x plus 5 plus square root of 5. At this point, again, you can cancel the x and x to get a simpler form, which is 1 over square root of x plus 5 plus square root of 5. At this point, you want to see if you can actually plug 0 into x to find the limits. You can, because it's not going to make the denominator equal to 0. So the last step is just plug 0 into x. You get square root of 5 plus square root of 5, right? Because it's 0, so it's just going to be 1 over 2 square root of 5, which is your answer. So I just illustrated an examples of how we can use the rationalizing technique to find the limits of the functions when there's radical terms involved. All right, now let's go to the next example, example number 7. Let's try to find the limits of the functions x squared time to sine of pi over x when x goes to 0. So as a reminder that the function sine pi over x is an oscillating functions, and the limits of these functions when x goes to 0 doesn't exist. Okay, so that means we cannot use the product rule to find the limits of these functions, because you have x squared times sine of pi over x. Since the limits here doesn't exist, so we cannot use a product rule. So what else we can use? So let's look at this graph. So this is the graph of the functions x squared sine of pi over x. And you can see that this is oscillating functions, right? And you see the functions oscillating rapidly as x goes to 0. Somehow, we can guess that the limit of this function when x goes to 0 should be 0. But how do we know that? Now, let's look at this function's x squared. So the function x squared is a function where it's always greater than most in this interval from -1 to 1. From 1 to 1, from -1 to 1, the purple function is always greater than the green functions. That's right. If you look at the function's negative x squared, there's a blue graph right here. And from the interval from -1 to 1, again, the blue graph here, x equals y equals negative x squared, is always less than the green graph. And you can see that the green graph here is squeezed between the two functions, between the two graphs, the purple one and the blue one. And they are squeezed, so these two graph, purple and blue graph, squeeze the green graph at x equal to 0 at one point here. So you can see that if you have two other functions that squeeze one function in between, and then the limit of x squared and the limit of negative x squared when x is 0 equal to 0, then you can conclude that the limit of the green functions here when x goes to 0 is 0. Here's a graph of, let's say this is the graph x squared, and this is the graph of negative x squared, and this is the graph of the functions x squared sine of pi over x. Okay, and the green function is squeezed between these two graphs, these two functions, and then if the limit of these two functions x squared and negative x squared equals the same when x goes to 0, then we can conclude that the middle functions x squared times sine of pi over x also has a limit when x goes to 0 is 0. Okay. So that is the squeeze theorem, actually. And the squeeze theorem tells you that if you have three functions, h of x is less than or equals f of x, less than or equal g of x, that means the function f of x is squeezed in between h of x and g of x. For all x in an open interval containing the value c, then except possibly at c itself, right? And if the limit of the function h of x when x goes to c is the same as the limit of the function g of x when x goes to c equals to a value, a real value L, then you can conclude that the limit of the function, the middle function f of x when x goes to c does exist and also equals to L. So the limit of these three functions will be equal to the same as L. That's a squeeze theorem. So in order to use a squeeze theorem, you have to find the two functions h of x and g of x that squeeze the middle functions, right? And also another condition is the limit of these two bound functions has to be the same when x goes to c. And c has to be, and these conditions here is satisfied within an open interval that containing c. Oh, sorry. Now we look at a different, let me see. This is a different graph of three different functions. So the green functions here is a function y equals to 1. The blue functions is a function y equals to cosine of x. And the red function is a function actually sine of x equals to x. So if we know that this red function is squeezed in between the green and the blue functions, and we know that the limit of y of 1 when x go to 0 is 1. And the limits of the cosine of x when x goes to 0 is also 1, right? And these two functions here is squeezing this red function. So by the squeeze theorem, you can conclude that the limits of the function sine of x over x when x goes to 1 is also 1 by the squeeze theorem. At first, you cannot do that because you cannot plug 0 into x, right? But then using the squeeze theorem, the limit of the function sine of x over x when x goes to 0 equals to 1. And this is one of the special limits that we can use the result in order to find limits of other function that involves one of these functions. All right, so the first special limits is the limits of sine of x over x when x goes to 0 equals to 1. The limits of 1 minus cosine of x when x goes to 0 equals to 0. And the limits of 1 plus x raised to 1 plus x. No, the limits of 1 plus x raised to 1 over x when x goes to 0 is e, which is an Euler's number. So these are the three special limits I hope that you keep in mind when you have to evaluate other functions that somehow involve one of these functions. And you can use a special limit to evaluate other functions. Let's do the next example, the first example on the third exercise. You want to find the limits of the functions sine square x over x when x go to 0. Again, you cannot plug 0 into x because it's going to make the denominator go to 0. Let's see what else we can do. You see, like sine x over x. It's very, that reminds us the special limit sine of x over x when x goes to 0, right? And it should be 1. So this is the special limits that we can use the result of this special limit. But we have x squared. How can we squeeze the x sine of x over x out of the x squared sine square x over x? We can just need to break it into two different identical function, which is sine of x. And then, as you know that we can break this into two different functions, right? Times the limit of x goes to 0 sine of x. In this case, we can use the product rule. It's because the limits of the function sine of x over x does exist and is equals to 1. And the limits of the function when sine of x when x goes to 0 is just 0. Sine of 0 is 0. Sorry. All right, and then your answer should be, oh, no, not 1. Should be 0. Now go to the next example. Again, we cannot plug 0 into x because x is the denominator. And then we also see this is a similar form to the special limits, right? Of sine of x over x equals 1. This is a special limit again. It's similar, it's not the same, but how can we squeeze the sine of x over x out, or how can we approach these problems? So from these special limits, you can infer that if you have sine of a different variable, let's say sine of a square, then if you divide it by a square, you still get 1. that means whatever you have in this input form, and if you divide it by the same thing in denominator, then you can actually use this limit, special limit, and you can use the result of the special limit. So let's go back to our problem. Here, when we have x so to 0, you have sine 7x. And in order to use this special limits, you need to have 7x in your denominator, right, to use it. But you don't have 7x, you only have x. That means you have to multiply 7 to the bottom. That means you have to multiply 7 to the top in order to get 7x in the numerator, in the denominator. Okay, so you multiply 7 to the top and 7 to the bottom just to reserve the equivalencies of the original functions. But then from here, we can squeeze this sine of 7x over 7x. And this constant here, we can move it to the front because it's just a constant. And then we can use the special limit to find this limit, which is just 1. And then the answer is 7. So this is how you use this special limit slightly in different ways to find limits of these two problems.